In a recent study, 70% of unmarried men live to age 65.
Right, that is a real statistic.
But for married men, that survival number jumped up to 90%.
Wow, yeah, that is a really big jump.
It is. So does marriage act like a magic shield for a longer life?
Well, maybe. Or there is a hidden story inside those numbers.
That is exactly the kind of question we want to answer today.
Yes, welcome to our deep dive into engineering statistics. We are so glad you are listening.
We really are. Today, we will explore how engineers use numbers.
Right, they use numbers to make really smart decisions.
Now, I know many people feel very nervous about this.
Oh yeah, they hear the word statistics and get scared.
Exactly. They imagine dark chalkboards,
Filled with very long and confusing math equations.
Right. But do not worry, we will not use hard math today.
No confusing technical words either, just very simple English.
We will use clear ideas to explain everything to you.
So let us start. What is statistics, really?
Well, statistics is basically the helpful language of data.
Right, and data simply means useful information.
It is information that helps us understand our daily reality.
Engineers use the science to collect and organize that information.
Yeah, and then they analyze it to solve complex problems.
Exactly. They use it to build much safer machines for us.
Now, statistics really does two different jobs in the real world.
Yes, it does. The first job is called descriptive statistics.
Descriptive statistics. Okay, what does that mean?
It means summarizing data to understand what is happening right now.
Let us go back to that study about the married men.
Okay, the survival study.
Right. Saying 90% of married men survived is a fact.
Exactly. It is a simple descriptive fact.
It just tells us what happened to those men in the past.
Yes, but what if I say being married helps men live longer?
Well, that sounds like a much bigger guess.
It is. You are making a guess about the whole world.
Right. So that is not just a simple fact anymore.
Exactly. That is the second job, called inferential statistics.
Inferential statistics. That is a big word.
It just means you are making a smart guess about the future.
Oh, okay. You use small facts to predict things for a larger group.
Yes, exactly. The first statement is just a fact from the study.
And the second statement is a big predictive leap into the future.
Right. But to make that predictive leap, we need a starting point.
Yeah, we need to know exactly where our information comes from.
Because before we can analyze information, we must collect it first.
I mean, we must understand our ingredients before we bake the cake.
I love that comparison. That is exactly right.
So how do we collect this information in the real world?
Well, we cannot measure every single machine in the whole world.
No, of course not. That would take forever.
Right. That giant group of everything is called the target population.
The population. Okay, so that means absolutely everyone or everything.
Yes. So instead of that, we measure a small and specific group.
And what do we call that small group?
We call that small group a sample.
A sample. So it is like tasting one spoonful of soup.
Yes. That is a perfect example for our listeners.
I taste one spoonful to know if the whole pot tastes good.
Exactly. You do not need to drink the whole pot of soup.
Right. One spoonful tells me the flavor for the whole dinner.
Engineers do the exact same thing with their new products.
They use small samples to guess facts about the giant population.
Yes, and this smart method saves the company huge amounts of time.
Okay, but who actually scoops that small spoonful out of the pot?
That is a great question. How do we physically gather this data?
Yeah, how do I get the numbers from my busy factory?
Well, we have two main ways to gather our working data.
Okay, what is the first way?
The first way is officially called primary data.
Primary data. So that means I do it myself.
Yes, exactly. It is fresh information you collect yourself.
Like, if I directly watch a heavy machine working on the floor.
Right. Or you might interview a factory worker about their daily tasks.
Okay, so primary data is firsthand information. I get it.
Yes. Now, the second way is called secondary data.
Secondary data, let me guess. Someone else collected it.
You got it. It is older information someone else already collected.
Like an old internet database. Or maybe a past business report.
Exactly. You use it, but you did not collect it yourself.
Okay, so now we finally have a big list of fresh numbers.
Right. But a messy list of random numbers is completely useless.
Yeah, looking at a list of 1,000 numbers gives me a headache.
Exactly. That is why engineers must organize that giant, messy pile.
How do they do that? Do they sort them out?
Yes. We turn ungrouped raw data into neatly grouped data.
Group data, what does that look like?
Well, we sort all those numbers into specific size ranges.
Oh, the notes call those size ranges bins.
Yes, bins. Imagine sorting a giant bucket of mixed coins on your table.
Okay, I have a big pile of different coins.
Right. You put all the small coins into one specific wooden box.
And then I put all the large coins into a different wooden box.
Exactly. Then you just count how many coins are in each box.
So we just count how many numbers fall into each separate bin.
Yes. This simple counting action makes the hidden patterns easier to see.
That makes perfect sense. Sorting makes the mess clear.
It really does. But before we draw any visual charts, we must pause.
Why do we pause? We have our neat boxes of numbers.
Because we need to know what kind of data we actually collected.
Oh, right. Different types of information need different math rules.
Exactly. An engineer always asks one very important question first.
Are we measuring descriptive words or are we measuring real numbers?
Yes. Let us start with the descriptive words.
Okay, what do we call data that uses words?
We call it qualitative data.
Qualitative data. So it describes qualities or physical traits.
Right. It deals with traits instead of calculated math numbers.
Inside this qualitative group, the notes say we have nominal data.
Yes, nominal data. Nominal simply means the named categories have no order.
No special sorting order, like human eye color.
Exactly. Blue eyes are not mathematically better than brown eyes.
They're just different descriptive categories.
Right. But wait, I have a tricky question for you.
Oh, okay. Go ahead and ask.
What about machine identification numbers, like machine 402?
Oh, I see. Machine 402 has a number in its name.
Right. So why is a machine number not considered a math number?
Well, I think because it is just a naming label for the object.
Yes. You do not add or subtract machine numbers together.
Right. Machine 1 plus machine 2 does not equal machine 3.
Exactly. Because we do not do math with it, it remains qualitative.
That is a great way to remember it. Very helpful.
Next, we have ordinal data inside the same qualitative group.
Ordinal data. That sounds like the word order.
You are so smart. Yes, it means the categories have a strict order.
A meaningful rank, like product quality ratings.
Exactly. Ratings like good, better, and best are ordinal data.
The specific rank tells a clear story about the final product.
Right. Best is clearly higher ranked than good.
Okay, so that is words and ranks. What about real numbers?
Now we move to the category called quantitative data.
Quantitative. That means quantities or numerical data.
Yes. This deals with measurable quantities and real math numbers.
And we have two different types of numerical data here, right?
We do. First, we have simple discrete data.
Discrete data. That means distinct whole values, correct?
Exactly. Whole values that you can easily count one by one.
Like you can count the exact number of broken machines today.
Right. Or the total number of safety accidents this year.
Because I cannot have half of an accident. It is a whole event.
Exactly. The second type is called continuous data.
Continuous data. That sounds like it keeps flying.
It does. It can be broken down into tiny invisible decimal fractions.
So it measures things like human body weight or total part length.
Yes. Let me make sure this is simple for everyone listening.
Okay, let us test my understanding of these two types.
Great. Say you count 3 broken machines in the factory.
That is definitely discrete data. I count whole machines.
Right. Now, what about the air pressure inside a large tire?
Well, the tire pressure can be 33.5.
Exactly. It has a decimal point.
So that is continuous because it flows infinitely between whole numbers.
You summarized the core difference perfectly. Great job.
Thank you. So now we know if our data uses categories or flowing numbers.
Right. And because we know this, we can choose the right colorful chart.
Oh, I love charts. Looking at typed numbers is just confusing.
Yes. Charts make complex data instantly understandable for everyone.
If you manage a large team, you absolutely need quick visual charts.
You simply do not have time to read 1,000 daily reports.
No way. That is why choosing the correct visual chart is so important.
Let us start with visualizing our qualitative data first, the categories.
Okay. What is the best chart for categories?
Well, pie charts are best for showing different parts of a whole object.
A pie chart. It looks exactly like a round pizza, right?
Yes, a pizza cut into different slices.
But I remember there was one strict mathematical rule for pie charts.
Oh, yes. Very strict. All the pizza slices must add up exactly to 100%.
Right, you cannot have 110% of a pizza.
Exactly. Now, we also use rectangular bar charts for categories.
Bar charts. They compare different categories side by side on a page.
Right. But there is a rule here, too. There must be distinct empty spaces.
Empty spaces between the tall, drawn bars.
Yes. The gaps show that the categories are completely separate things.
That makes perfect sense. Red apples are not yellow bananas. They need space.
Exactly. So what charts do we use for smoothly flowing continuous data?
Well, the notes mention special charts called histograms.
Yes, complex histograms. A histogram looks very similar to a bar chart.
Wait, it looks just like a bar chart to me. They both have tall rectangles.
They do, but look closer at the histogram.
Oh, the tall rectangular bars are physically touching each other. There are no gaps.
Right. Why do you think the histogram bars touch each other like that?
Because continuous data flows seamlessly without any hard stops or breaks.
You got it. Tire pressure flows smoothly from one number to the next.
So because the data flows without breaking, the chart bars must also touch.
That is exactly right. We also use simple line graphs for continuous data.
Line graphs. Are those best for showing numerical changes over long times?
Yes. You might track the number of daily earthquakes with a line graph.
Okay, I also saw frequency polygons mentioned in our source materials.
Yes, polygons are quite simple, actually.
How do they help us see the data story?
Well, polygons simply connect the middle points of the touching histogram bars.
Oh, so they just draw a line connecting the tops of the bars.
Exactly. They quickly show the simple outer shape of the data for us.
What about ogives? That is a very strange word.
Ogives track a continuous running total as the gathered numbers grow larger.
A running total. So it just keeps adding up.
Yes, this running total clearly shows how many things fell below a target.
Oh, that sounds very useful for safety checks.
It is. Now, there is one more important chart called a box plot.
A box plot. Why do smart engineers love using this special chart?
Because a box plot uses a special 5-number snapshot of your data.
5 numbers, what are they?
It shows the absolute minimum value and the absolute maximum value clearly.
Okay, the lowest number and the highest number. That is 2.
Right. It also shows the lower quartile and the upper quartile.
That sounds a bit complex. What is a quartile?
It just means the quarter marks, the 25% and 75% marks.
Ah, I see. And what is the final number?
Finally, it shows the median or the exact middle of the data.
Okay, so minimum, lower quarter, middle, upper quarter, and maximum.
Exactly. But the real magic of this chart is the drawn box in the middle.
What does that drawn box show us?
This box shows exactly where the middle 50% of data safely lives.
The middle 50%. So that is where most of the normal stuff happens.
Yes, we call this middle section the simple interquartile range in our field.
Interquartile range. Okay. Why is that specific box so helpful?
Engineers love it because it instantly highlights dangerous hidden outliers.
Outliers, you mean numbers that are way too high or way too low?
Exactly. It helps you find the faulty machine much faster.
That is amazing. But, drawing the colorful chart is really only half the job.
You are right. Now we have to look closely at the shape of the drawing.
The visual shape of the data tells a very secret story, doesn't it?
It really does. It diagnoses exactly what is happening inside the real factory.
So let us look at some specific shapes. What is the first one?
First, let us look at perfectly smooth, symmetrical patterns in data.
Symmetrical. That means both sides look exactly the same, like a mirror.
Right. The most famous one is the beautiful bell-shaped visual distribution.
Bell-shaped. It looks exactly like a smooth mountain peak in the center.
Yes, a perfect mountain. The key trait here is how the mean and median act together.
The mean is the calculated average, right?
Yes. In a bell shape, the average mean equals the exact middle median point.
So they are exactly the same number.
Right. Let us pretend my data set has a calculated average mean of 12.
Okay, the mean is 12.
And it also has an exact middle median point of 12.
Because they match, that means I probably have a perfect bell-shaped mountain peak chart.
Exactly. That is a great simple system check for your data.
Are there any other symmetrical shapes?
Yes. Another symmetrical shape is called the uniform distribution.
Uniform? Does that mean it looks the same everywhere?
Yes. The data is completely flat because every group has equal frequency.
It has no mountain peak at all, just a flat line.
Right. But what happens when the data is not perfectly symmetrical anymore?
When the mountain's leaning over to one side.
Yes. We call that leaning shape a skewed distribution in our field.
Skewed. Okay, let us talk about a right skewed shape.
A right skewed shape has a long tail stretching far to the right.
So the peak is on the left and the tail goes right.
Exactly. The heavy data cluster is very closely on the left side.
What does that long right tail do to the math?
Well, those extreme high numbers pull the calculated average mean way up higher.
Oh, so the mean becomes much greater than the middle median point.
Yes, you got it perfectly. Now, what about a left-skewed shape?
I bet it is the exact opposite.
It is. A left-skewed shape has a long tail stretching to the left.
So the heavy data cluster is very closely on the right side.
Right. Extreme low numbers pull the calculated average mean way down lower.
So the mean becomes much less than the middle median point.
Exactly. The long stretching tail always pulls the math in its own direction.
That is a very easy rule to remember.
It is. Now, are there any complex shapes that tell a strange hidden story?
Let us see. The notes mention a special U-shaped distribution.
Yes, the U shape. It is very high at both extreme outside ends of data.
High on the left and high on the right.
But it is very, very low in the exact middle point area.
That is a weird shape. What kind of real data looks like a U?
Well, customer satisfaction reviews are a great example of this specific shape.
Oh, that makes sense. People only leave reviews if they truly loved or hated a product.
Exactly. They rarely leave reviews if the product was just perfectly okay.
Right. I mean, I only write internet reviews when I am really angry or extremely happy.
See, that U shape makes perfect logical sense for basic human behavior.
It really does. Okay. What is the final complex shape we need to know?
The final complex shape is officially called the bimodal distribution.
Bimodal. Bi usually means two, right? Like a bicycle has two wheels.
Yes. Bimodal simply means the gathered data has two completely separate tall peaks.
Two peaks.
Yeah.
So it looks exactly like a desert camel with two humps on its back.
That is a perfect visual image, a camel with two humps.
Well, two tall peaks on the chart sounds like really great news to me.
Wait, why do you think it sounds like great news?
It must mean we're producing twice as many good products. Two peaks means great success.
Actually, no. In engineering, this is an important and very dangerous warning sign.
Really? A dangerous warning sign. Why is it bad?
Two peaks usually mean you accidentally mixed two completely different populations together.
Oh, I see. So it is not one consistent process.
Exactly. You might be measuring parts from two totally different working machines.
So machine A makes small parts and machine B makes large parts.
Right. And you mix them together. It means your engineering process is not safe anymore.
Because mixing different things causes bad confusion for the busy factory workers.
Yes. Consistency is the most important thing for an engineer.
That makes total sense now. So we have covered so much ground today.
We really have. This brings us to the ultimate goal for the smart engineer.
Yes. Let us quickly review the simple 5-step workflow for the modern engineer.
Okay. Step 1 is to identify your specific data type very clearly.
Right. Is it words or is it flowing numbers?
Exactly. Step 2 is to organize and group your messy data into bins.
Put the coins into the right wooden boxes.
Yes. Step 3 is to visualize and draw the completely correct chart.
Pick a pie chart or a bar chart or a histogram.
Right. Step 4 is to diagnose the hidden shape of your visual data.
Look for the mountain peak or the camel humps or the long tails.
You are doing great. And step 5 is to infer the deeper meaning for the real world.
Make that smart guess about what will happen tomorrow.
Exactly. That is the whole workflow from start to finish.
You know, statistics is really not about scary math or confusing technical words at all.
It really isn't. It is just a helpful tool to turn numbers into clear visual insights.
It helps us make smart, safe decisions based on solid scientific evidence.
Right. And it takes away the guessing game for big companies.
We learned today that statistics helps us predict what might happen tomorrow.
Yes, we predict the future based on the careful data we collect right now.
But I want to leave you, our listener, with a final thought today.
Oh, a final question for them to think about.
Yes. What happens when the carefully collected data is missing something important?
That is a very interesting question.
How much of the real future is hidden in unmeasured, missing numbers?
Wow. If we do not measure it, we cannot see it.
Exactly. Keep asking those big questions as you explore your complex world.
Thank you so much for joining us on this journey.
Yes. Thank you for listening. Keep learning, and we will see you next time.